Hello, good morning, all of you. This is Dr. U. Raghavendra, Assistant Professor of Chemistry, MVS Government Degree and PG College, Mahabub Nagar, Telangana. Today, I want to discuss about part 2 of amines. In my last video, I explained about the part 1 of amines. In that video, I explained about the introduction, classification, and preparation methods of amines. In the present video, I want to discuss about the other things related to amines. Okay, fine. Next, in this video, I want to discuss about the physical properties of amines, basicity of amines, as well as the use of quaternary ammonium salts as PTCs, that is phase transfer catalyst, that is how the quaternary ammonium salts acts as phase transfer catalyst. Okay, fine. Next, physical properties. In physical properties, first one is state or physical state. Generally, if you observe the state of the amines, in the case of aliphatic amines with lower number carbons, less or lesser number carbons, that is mainly the aliphatic amines up to 3 carbons generally exist as gaseous molecules with fishy smell. That is, lower aliphatic amines exist as gaseous molecules with fishy smell. The aliphatic amines or the primary amines with more than 3 or 4 carbons, that is the aliphatic amines with more than 4 or more than 4 carbons generally exist as liquids at room temperature. That is, below 4 carbons they are in gaseous state, above 4 carbons they exist as liquids at room temperature. The smell of the higher amines, that is having more than 4 4 or more than 4 carbon atoms, generally it is ammonious smell. The lower aliphatic amines generally fishes have fishy smell, but the higher aliphatic amines, that is having more than 3 carbon atoms, contains ammonia smell. The other amines, that is the higher amines, which have generally the carbon atoms above 10, generally exist as in the form of solids at room temperature. That is, amines exist in 3 states. Lower number is up to 3 carbons, they exist in gaseous state. The medium one exists in liquid state. The higher one exists in solid state at room temperature. In the case of aromatic amines, that is the starting aromatic amine is aniline, where it is pH NH2, that is NH2 group is directly attached to benzene ring. That is all aromatic amines, it may be aniline or any aryl amines, generally they are colorless liquids. They are colorless liquids at room temperature. But if we expose the aromatic amine to environmental oxygen, then they get colored due to the oxidation of nitrogen atom. That is, normally or in closed conditions, the aromatic amines are colorless liquids. If you expose them to environmental oxygen, due to the oxidation of aromatic amine, they converted into colored compound. Okay, fine. Next, hydrogen bonding. Hydrogen bonding is nothing but it is the one type of chemical bond which takes place in between more electronegative atom and hydrogen atom of the same molecule or different molecules. If the hydrogen bond formation takes place within the molecule, then it is considered as intramolecular. If it is in between the molecules, then it is considered as intermolecular hydrogen bonding. The case of amines also, amines molecules forms hydrogen bond in between the two amine molecules. As we discussed in my part 1 video, amines classified into mainly three types. They are primary amine, the general formula is RNH2. Secondary amine, the general formula is R2NH. Next one is tertiary amines, the general formula is R3N. Here, based on the number of hydrogen atoms present on the nitrogen atom of the amine, they form respective number of hydrogen bonds. So in the case of primary amines, the primary amine contain two hydrogen atoms attached to nitrogen atom. That is, according to general formula, it is RNH2. So the primary amine contain two H2, two hydrogens atoms. So primary amine can form two hydrogen bonds with other amine molecule. Here, hydrogen bond formation is due to the polar nature of NH bond. Here, nitrogen is more electronegative atom than the hydrogen. So, the NH bond electrons shifted towards the nitrogen atom. So, due to this shifting, the nitrogen atom gets partial negative charge. Then the hydrogen atom gets partial positive charge. That is, the amines are polar molecules as alcohols or other polar molecules. So they easily forms hydrogen bonds with the same amine molecule or with other molecules. Primary and secondary amines generally involves in intermolecular hydrogen bond formation due to the presence of two hydrogens and one hydrogen respectively on primary and secondary amines. Here, due to the hydrogen bond formation or intermolecular hydrogen bonding in primary amine and secondary amines, the amines get associated together. But in the case of tertiary amines, due to the lack of hydrogen atom on tertiary amine, they don't involve in hydrogen bonding. That is, in intermolecular hydrogen bonding. So there is no intermolecular association in tertiary amines. That is, the tertiary amine molecule exists as the individual molecule. But in the case of primary and secondary amines, they associated together. Okay, fine. Next, we observe the hydrogen bonding in amine molecules. The first one is, sorry, here the first one is example for intermolecular hydrogen bond formation in primary amine, that is RNH2. RNH2 is primary amine. Here, due to the presence of two hydrogens, it forms two hydrogen bonds, and the nitrogen also involves with one more hydrogen bond with other amine molecule. So overall, the primary amine molecule forms three hydrogen bonds. Two are due to the two hydrogens and the remaining due to the nitrogen. Okay, fine. This is intermolecular hydrogen bond formation in between the secondary amine molecules. Here it is secondary amine, that is R2NH. Here also it is secondary amine. Due to the presence of one hydrogen atom, it involves in intermolecular hydrogen bond with one more amine molecule. Here nitrogen also involves in one more hydrogen bond, that is secondary amine forms two hydrogen bonds. Primary amine forms three hydrogen bonds with three other primary amine molecules. But in the case of tertiary amine, that is R3N, it don't form any hydrogen bond due to lack of hydrogen atoms. Okay, next. Here also the image reflects or indicates the hydrogen bonding, that is inter- intermolecular hydrogen bonding in primary amine, it is RNH2. It forms intermolecular hydrogen bond with other RNH2, other RNH2, as we discussed here. Okay, fine. Next, boiling points. Boiling point is nothing but it is the temperature or the minimum temperature required to raise or to boil the liquid, that is the minimum temperature at which the liquid starts converting into vapor state, generally known as boiling point or boiling temperature of that particular liquid. In the case of amines, which can form hydrogen bonds, in the case of amines, the hydrogen bond is responsible for differences in boiling points of primary and secondary and also tertiary amines. Due to the difference in formation of hydrogen bonding, there is also difference in boiling points of primary, secondary and tertiary amines. So based on the number of hydrogen bonds formed in the amine molecule, the order of boiling points in three types of amines is as follows. That is, primary amines have more boiling points than that of secondary. The secondary amines in turn have more boiling points than the tertiary amine. It is due to the formation of intermolecular hydrogen bonds. Due to the intermolecular hydrogen bonds in the amine molecules, they get associate together. That is, all the molecules interconnected to each other through intermolecular hydrogen bonding. So in order to separate or in order to evaporate the liquid, we have to supply large amount of thermal energy. So the boiling points are very high in the case of primary amine than the secondary amine. In secondary amines, means the boiling points are very high than the tertiary amine. In the case of tertiary amine, there is no hydrogen intermolecular hydrogen bonds, so they have least boiling points. Okay, if you compare the boiling points of amines with other molecules such as alcohols, the boiling points of amines are less than that of alcohol molecules having same molecular weight. It is due to the difference in polarity of NH and OH bonds. Here, oxygen is more electronegative atom than that of the nitrogen. So, OH bond is more polar than that of NH bond. So, the intermolecular hydrogen bond formed in alcohols is stronger than that of the amine molecules. So alcohols MPBP values are higher than that of amines, corresponding amines which have similar molecular weight. Okay, fine. Next, solubility, that is dissolution of amines in water molecule. That is the solubility of amines in water. In the case of aliphatic amines, which have lower molecular weight, that is aliphatic amines or lower aliphatic amines generally dissolves in water due to the formation of intermolecular hydrogen bonds with water molecules. The dissolution of primary amine or aliphatic amine in water is due to the intermolecular hydrogen bonds with water molecules. But in the case of aromatic amines, the aromatic amine solubility in water is very less, or in some cases, they don't dissolve in water. It is due to they don't form, that is aromatic amines don't form intermolecular hydrogen bonds with water molecules, so they don't dissolve in water. Instead, they dissolve in organic molecules. Okay, fine. Here the image reflects, or sorry, resembles the intermolecular hydrogen bond in between the amine molecule and the water molecule. Here also water molecule. This is methyl amine dissolution in water molecule. Okay, fine. Next, basicity of amines. Before going to explain the basicity of amines, we should know the classification of substances. Generally, the substances classified into three types, mainly based on their nature. They are acids, second one is bases, third one is neutral molecules. Acids, in order to explain the acidic or basicity nature of compounds, there are three theories. One is Arrhenius theory, second one is Bronsted-Lowry theory, third one is Lewis theory. According to Arrhenius theory, the molecule which or the substances which release H plus ions in their aqueous solution known as acids. Similarly, the compounds which releases OH minus ions, that is hydroxide ions, in their aqueous solutions generally considered as bases according to Arrhenius concept. According to Bronsted-Lowry concept, the compounds which donate proton or H plus considered as acids, and the compounds which attracts or receives or accepts the proton generally considered as bases. That is, according to Bronsted-Lowry, proton donor is acid, proton acceptor is base. In the third classification, or in the according to third theory, that is according to Lewis theory, the compounds which have a capacity to donate lone pair of electrons generally considered as bases, while the molecules which have a capability to receive lone pair of electrons considered as acids. That is, they consider as Lewis acids and Lewis bases. That is, lone pair donor generally known as base, Lewis base, lone pair acceptor considered as Lewis acid. Here, the basicity of amines generally explains according to Arrhenius concept. That is, if the substance releases OH minus ions in its aqueous solution, then it is considered as base. Sorry, here the basicity of amines generally explain on the nature of donation of lone pair of electrons. That is, here the basicity is explained based on the Lewis concept, but not on the Arrhenius concept. Sorry. Here, in the case of amines, the nitrogen atom contains one lone pair of electrons, so it acts as a Lewis base by donating the lone pair of electron to the proton or any other electron deficient species. So, amines are Lewis bases. In general, in organic chemistry, amines are the fundamental bases. The best example for bases in organic chemistry are amines and amine derivatives. Okay, here the strength of the amine or the basic strength of amine is generally explained on its dissociation constant, that is based on the Kb value. Kb is base dissociation constant. Here base is amine. So how much or how easily the amine base undergoing dissociation in aqueous solution or by accepting proton from the water molecule. So, as shown here, the amine molecule interacts with water molecule to form corresponding alkylated ammonium ion. It is generally an equilibrium reaction. So, for this equilibrium reaction, we can derive an equilibrium constant. Here, the equilibrium constant is Kb, that is base dissociation constant. We can express Kb as constant, the product of concentration of alkylated ammonium ion and hydroxide ion divided by concentration of primary amine or amine, which is taken here for the study. If the numerator value is high, that is if the equilibrium reaction shifted towards right side, that is forward reaction is major, then Kb value is high. If the Kb value is more, then the dissociation of the amine is high, that is the basic strength of the amine is also high. We can convert Kb value into pKb value as in the case of pH, where pH is equal to minus log H plus. Similarly, here pKb is equal to minus log Kb. Here the Kb and pKb values are inversely proportional to each other. If the Kb value is high, the basic strength of the amine is high, but for that amine where Kb value is high, then pKb value is small or very smaller value. That is, if the amine is strong base, then its Kb value is high or its pKb value is small. That is, stronger bases have smaller pKb values. Okay, fine. Next, what are the factors influencing basicity of amines? That is, the factor which are influencing the basicity nature of amines. There are, we can explain the basicity nature of the amines based on the two factors. One is electronic factor, the second one is steric factor. Electronic factor is generally any factor which enhances or which decreases the electron density on the nitrogen atom of the amine, considered as electronic factor. Electronic factor generally plays major role, or electronic factor is predominant factor in the case of non-polar solvents. So in the case of non-polar solvents, the basicity nature can be explained by using electronic factor. There is no steric factor in the case of polar. In the case of non-polar solvents, majorly it is due to electronic factor only. In the case of aliphatic amines, as the number of alkyl groups increases, the basicity also increases. That is due to the plus psi effect of alkyl groups, that is it is electronic factor. Due to the plus inductive effect of alkyl groups, they releases electrons toward the nitrogen atom of amine. Alternately, the electron density on the nitrogen atom increases, which in turn the lone pair of electron easily available to the electron deficient species, that is protons. So the electronic factor is predominant one in the case of nonpolar solvents. So in the case of aliphatic amines, they are primary, secondary, tertiary amines. In the case of primary amines, it contains only one alkyl group. In the case of secondary amine, it contains it contains two alkyl groups. In tertiary amine, it contains three alkyl groups. So the electronic factor or the inductive effect is more, the plus effect is more in tertiary amine, it is less in primary amine. So according to electronic factor, the basicity order of the amines, aliphatic amines in non-polar solvent is this one, that is tertiary amines have more basic than that of secondary, which in turn they are more basic than primary amines. Here the primary amines also more basic than ammonia, that is tertiary amines greater than secondary, which is greater than primary amine, primary amine further greater than the ammonia. So based on electronic factor, amines basicity explained in non-polar solvents. But in the case of polar solvents, the basicity order is generally or quietly different to this order. In the case of polar solvents, the order is quite opposite to the first one. In the polar solvents, such as water, the alkylated ammonium ion undergo solvation with water molecules. Okay, fine. Next, I want to go to next slide. Here, due to the solvation or association of water molecules around alkylated ion, then the stability of alkylated ammonium ion increases. That's why the equilibrium reaction, which is discussed in our previous slide, shifted towards the right side. That is, base dissociation is high, so the base will be strong. That is, if the solvation is high, then the stability of the alkylated ammonium ion also high, then automatically the equilibrium reaction shifted towards right side, so the base is, the amine is more basic. Here the solvation is nothing but association of water molecules around a particular ion. Due to the solvation, there is release of some energy, which is nothing but salvation energy. This salvation energy generally used to stabilize the alkylated ammonium ion or that particular ion. In the case of primary amines, due to the less steric hindrance, which contains only one bulky alkyl group, the solvation is more through formation of hydrogen bonds with water molecules. So the stability of primary alkylated ammonium ion is more. But in the case of secondary amine, due to the presence of two bulky alkyl groups, it is somewhat difficult to associate with water molecules. That's why the solvation energy is less. So the stability of dialkylated ammonium ion is less. So the basicity of secondary amine is somewhat less than that of primary amine. In the case of tertiary amines, it contains three bulky alkyl groups, so it is further difficult to associate with water molecules. That's why the solvation energy is very less when compared to with secondary amines and primary amines case. So the trialkylated ammonium ion is less stabilized by solvation process or solvation energy. Here, due to the presence of three alkyl groups as well as due to lack of hydrogen atoms, it don't get association with water molecules. So tertiary amine basicity is less when compared to secondary amines, which in turn less than that of primary amines. So in the case of polar solvents such as in water, the basicity order is quietly opposite to that of the the non-polar solvents order. In the case of polar solvents, the order of basicity of amines is secondary, secondary, primary, tertiary, and ammonia. Here, according to solvation energy, the primary amines must have higher basicity than secondary. But here the secondary amine is more basic than the primary amines due to it contains only two alkyl groups. Here salvation also possible as well as electronic factor also possible. So secondary amine is more basic than the primary. Primary is more basic than the tertiary. Here the in the case of tertiary amines, steric factor dominates the electronic factor, so its basicity is less. That is, secondary is more basic than the primary, which is in turn more basic the tertiary. The least one is ammonia. Okay, fine. Next, if you compare the basicity of aliphatic and aromatic amines, generally here the basicity order or the basic character of amines is generally depends on the sorry on the electronic density or electron density of the nitrogen atom of the amine. If the electron density is high, the basicity of that particular amine is very high. So in the case of aliphatic amines, the alkyl groups are they are in the case of aliphatic amines, the alkyl groups shows plus I effect. That's why they enhances the electron density on nitrogen atom, so the basicity increases in aliphatic amines due to the substitution of alkyl groups. So tertiary amine is more basic than the secondary than the primary, the case of non-polar solvents. But in the case of polar solvent, it is quite different. In the case of aromatic amines, here the nitrogen of amine group attached to or directly attached to arene ring or benzene ring, which shows minus I effect. That's why the electron density on nitrogen atom is less available to the electron deficient species. So the basicity of aromatic amines is less than that of the aliphatic amines. The other reason is here the lone pair of electrons present on nitrogen atom of aromatic amine undergo delocalization and they undergo delocalization with iron ring. So the basicity of aromatic amines is less than that of the aliphatic amine. So the order is aliphatic amine is more basic than the aromatic amines. In particular, in the case of aromatic amines, if you substitute the hydrogens of NH2 group of aromatic amine, The formula is PHNH2, primary amine, aromatic primary amine. If you replace the hydrogens with other aryl groups step by step, then the the basicity of that particular aromatic amines decreases gradually due to the substitution of more electron withdrawing aryl groups. So the the basicity order of aromatic amines is the dialkyl aniline is more basic than monoalkylated aniline, which is in turn more basic than the aniline. Here the aniline is more basic than the diphenyl diphenyl aniline, which is more basic than the triphenyl aniline. That is, by substituting the hydrogens of NH2 group of aromatic amine with all electron donating groups, the basicity increases, but the basicity decreases by substituting with phenyl or any aryl groups. Okay, fine. Next. Next, use of quaternary ammonium salts as phase transfer catalyst PTCs. Generally, what is phase transfer catalyst? Catalyst is nothing but it is a third substance which enhances or decreases the rate of reactions by changing the path of the reaction mechanism. That is, the third substance other than reactant molecule which alters the rate of reaction, may increase or may decrease, considered as catalyst. Here phase transfer catalyst is catalytic reactions are a specific type of heterogeneous catalysis. Generally catalysis is two types. If the reacting phases and the catalyst are in same phase, then it is known as homogeneous. If they are in different state phase, sorry, if they are in different, that is reactants and catalyst are in different phases, then it is considered as heterogeneous catalysis. Here phase transfer catalysis is example for heterogeneous, or it is a specific case of heterogeneous catalysis. Here, in the case of organic chemistry, generally organic reactions takes place in between the reactants molecule in the presence of some catalyst, or they may own. If in order to occur a reaction, a particular reaction, then the reacting phases must be in same phase, then only the reaction takes place. If the two reacting phases are in different phase, then there it is difficult to occur the reaction. In such case, we want to add some third substance which reacts with both reactants present in different phases. In organic reactions, the organic compounds undergo reaction with ionic compounds. Here the ionic compounds generally dissolves in aqueous phase, but they don't dissolve in organic phase. So it is difficult to carry out the reaction. So in order to perform that particular reaction where the reactants are in different phases, that is, one is in aqueous media, one is in organic medium, then we have to add a catalyst which can transfer the reactant species or the reactant molecules from one phase to other phase in order to carry out the reaction, generally considered as phase transfer catalyst. Okay, that is phase transfer catalyst transfers the reactant from one phase to other phase where the reaction occur. This is about the introduction about the phase transfer catalysis or phase transfer catalyst. So in majority organic reactions, the reaction generally takes place in between the organic phase and aqueous phase, which are don't miscible each other. So we have to apply some phase transfer catalyst in order to perform that particular reaction. Okay, fine. Next, examples for phase transfer catalysts, PTCs. Here the quaternary ammonium salts as well as phosphonium salts and crown ethers, cryptans, or they are best examples for phase transfer catalysts. Here crown ethers are they are cyclic ethers. Cryptans are also one type of cyclic compounds having nitrogen and oxygen heteroatoms in the cycle. They also act as phase transfer catalysts. Phosphonium salts also acts as phase transfer catalyst. Among these phase transfer catalysts, quaternary ammonium salts are best one because they are cheaper and also suitable to perform organic reaction or a chemical reaction which takes place in between aqueous and organic phases. Okay, here if you observe the principle, generally uh, the principle is already discussed in the previous slide. Here the phase transfer catalyst generally has a capability to transfer the reactant molecule or reactant species from one phase to other phase where the reaction takes place. Then only the reaction occurs. In general, the reactant molecules which present in different phases, that is for example in aqueous and organic phase, if you mix the two reactant phase, then the reaction don't take place. But if you add a catalyst, that is phase transfer catalyst, which is capable to interact with organic as well as aqueous phase, then the reaction is undergo smoothly due to transfer of reactant species from one phase to other phase where the reaction takes place. This is the principle involved in the phase transfer catalyst. Okay, fine. Next, here what is the mechanism of phase transfer catalysis or catalyst? Here the quaternary ammonium salts generally act as best phase transfer catalysts. So here the quaternary ammonium salts, that is R4 n plus x minus, the formula is R4 n plus x minus. Here the quaternary ammonium salts contain hydrophilic as well as hydrophobic parts, so it can dissolve in organic phase due to the presence of hydrophobic part, that is R4, as well as it dissolves in aqueous medium due to the presence of hydrophilic part, that is n plus x minus, that is ionic spaces generally dissolves in aqueous medium, but they don't dissolve in organic medium. So if the reactants are in different phases, for example in they are in sorry they are in organic as well as in aqueous phase, then The reaction takes place through addition of phase transfer catalyst. If the reaction, if we want to perform a reaction in between alkyl halide and something that is m plus y minus, if we want to perform reaction between m plus y minus and rx minus, here the rx alkyl halide generally it is organic compound, so it dissolves in or it is in organic phase, but m plus y minus it is ionic compound, so it is easily soluble in water, so it exists in aqueous space. So if you add these two compounds, aqueous solution of m plus y minus to rx solution, the reaction don't take place on its own due to the immiscible nature of rx and m plus y minus. If we add a quaternary ammonium salt q plus x minus, then the reaction takes place. The first step, the q plus x minus enters into aqueous space and interacts with y minus m plus and forms an ionic pair, that is q plus y minus. This ionic pair then enters into organic phase due to the presence of organic part or hydrophobic part. After enter into organic phase, it interacts with alkyl halide to form corresponding product, that is ry, and the q plus x minus y, sorry, q plus x minus regenerated, that is the catalyst regenerated in organic phase. This regenerated PTC, phase transfer catalyst, then shifted to aqueous phase, then it undergo other reactant molecule, then forms ionic pair, then it enters into organic phase and reacts with other alkyl halide molecule to form product. That is the cycle continues till the end of the reactant molecules. Okay, fine. Next, if you observe some specific examples for phase transfer catalysis reactions or phase transfer catalyst reactions. The first one is reaction in between cyclohexene and chloroform CHCl3 in the presence of base NaOH. If you add cyclohexene and chloroform uh, in the presence of base solution, the reaction don't take place to form the product, that is 1,1 dichloro cyclopropene hexene, that we don't get this product due to the direct addition of cyclohexene and chloroform in the presence of base media. Here in this reaction, the reactant species is dichlorocarbon, that is CCl2. CCl2 content lone pair. It is the reactant species. It is generated due to the interaction of base with chloroform. Here chloroform is organic substance, base NaOH is aqueous substance. So they don't intermix each other. So there is no generation of CCl2 or dichlorocarbon. So the dichlorocarbon don't interact with cyclohexene. In order to generate dichlorocarbon CCl2, we have to add a phase transfer catalyst, that is quaternary ammonium salt. This quaternary ammonium salt transfers the base, that is hydroxide ion, from aqueous solution to organic solution. That is, here the aqueous solution contains water and base. The organic solution contains chloroform and cyclohexene. By adding quaternary ammonium salt, then it first dissolves with aqueous solution, then forms an ion pair, that is R4N plus OH minus, then it transfers to organic phase R4N plus OH minus. This OH minus interacts with chloroform to generate CCl2, that is dichlorocarbon reactant species. This dichlorocarbon undergo addition reaction with cyclohexene to form an addition product. This is the overall reaction, how it takes place through addition of quaternary ammonium salt. The other example is this one: 1 2 3 4 5 6 7 8 N-octyl bromide, reaction of N-octyl bromide with sodium cyanide. Here also sodium cyanide generally present in aqueous phase. The alkyl bromide is organic phase, so the reaction don't take place, but it occurs in the presence of addition of quaternary ammonium salt. By adding quaternary ammonium salt, it interacts with the sodium cyanide and forms a ionic pair with cyanide ion. This ionic pair with cyanide ion transfers into organic phase, where the cyanide ion interacts with the alkyl halide to replace bromide and to form corresponding cyanide product. This is all about phase transfer catalyst, how the quaternary ammonium salts helpful in occurring so many organic reactions. It is very useful in green chemistry, where the formation of byproducts is very less, and in green chemistry we can replace organic solvents by adding water in the presence of quaternary ammonium salts or phase transfer catalysts. So phase transfer catalysts are best one to prevent pollution or to prevent formation of unwanted byproducts. Directly we can get desired products. Okay, fine. Next. Thank you very much for your patience, for watching this video. Thank you all of you. Let us meet in my next video, that is part 3 of Amines, in which I want to, or I will discuss about the chemical properties of amines. Okay, thank you. Bye.